So I hope you can see my slides.
Yes.
Okay, perfect. So my name is Javier Camacho. I'm a PhD student at the Lund University and at the Danish Institute of Fire and Security Technology. And today's talk is going to be about uncertainty quantification. You can see that it's a quite long and sounds like a complicated name. I just try to simplify to call it a CFD, uncertainty quantification, but the proper title of the report is Intrusive Polynomial Chaos for Uncertainty Quantification on Supersensitivity in the Burgess equation using OpenFOAM. So let's go through will be an agenda with an introduction. Give a motivation of why I'm interested in this problem. Then a background on how to handle the problem, the existing and modified solvers that I have working on. And then, of course, at the end, cases where verification and uncertainty quantification will be explained. And then at the end, some conclusions on potentially future works. So some time ago, I come across this quotation. And then when I was doing this project, I was thinking, okay, but what else is inside of what we can read in between lines of this quotation about that all models are wrong, but some are useful. So I try to ask myself a question, and the question is about how we can quantify how useful or how well a model represents reality. And then to do that, I will try to go through a kind of a process that I will say most of you already know very well, but I try to reframe the same process in a little bit different diagram where I will include the uncertainty also. And I hope you can follow what I was trying to explain on this diagram. So normally when we do simulations, we have three main things, right? Reality. In reality, I mean actually the reality we are able to measure, like for example, experiments, the best of the representation of reality. Then a mathematical model. And of course, through this mathematical model, we have a numerical representation or implementation that can implement this mathematical model. And of course, this process is kind of iterative. If the reality or the way we are measuring become better, we need to reformulate our mathematical model maybe because we know a little bit more and so on. And it's the same thing with the numerical methods. So the process that goes through the different stages or phases, you can see is an analysis of the mathematical model with respect to the reality, then programming, and of course, simulation, right? And then with respect to the analysis is, of course, a model qualification to evaluate if we are not violating any physics that is already well known. And then at the end, what we have is what is called model validation, model verification. And if you can see, in between, I place uncertainty because we have uncertainty from the numerical part. We have uncertainty, of course, when we are doing the simulations itself, do it to the parameters uncertainty. And of course, we have also uncertainty from the reality we are measuring in the experiments. But the main idea of putting this diagram is not only about showing this process that, as I say, most likely you already know, but it's also about to clarify, because I encountered a lot of, I'm not saying misuse, but at least using interchangeable some terms. So I want to make a little bit an exercise because, at least in my case, for me, it's much easier to remember questions. So when we are thinking about verification, maybe it will be easier to remember that you can ask yourself, are we solving the equations right? And that will involve, of course, all the, when we are doing sensitivity analysis of the mesh, discretization errors, and so on. And then for the validation part, you can think about are we solving the right equations? And this is more toward to the physics and aligning with respect to the experimental the experiment that we are trying to compare with. And if you are more interested on that, you can go to the standards, the ASME standards for validation, verification and validation. And also I can recommend the Rocher perspective, which is actually a little bit in contradiction, or at least raising question that I think is quite useful, his book. And then final remarks in terms of verification and validation. When we are talking about verification, you can encounter kind of two main branches. One is the verification codes, and the other one is the verification of the calculation or the solutions, if we are solving them with the right methodology. And then another thing that I would like to point out, that if it's not experiments, validation cannot be performed in theory. So now moving toward to uncertainty quantification, which is actually the main topic of this presentation. When I was doing this project, as you can see, and I noticed already that there is three main fields that you need to deal with: engineering, computing, probability, and statistics. In this case, engineering was not that much because it's kind of a canonical problem, but still I was quite struggling or trying to figure it out how to deal with the probability and statistics that has been very long time ago that I have been working with. And of course, the computing part that is involving basically the core base of this course, which is OpenFOAM. So for uncertainty quantifications, as has been described by McLaren, we have 5 main steps: identifying the quantity of interest, modeling the uncertainty inputs, narrow down to the uncertainty, propagating, and assessing the impact. As you may imagine, as I said, this is a canonical problem, so identifying, modeling, and narrow down was not such as an issue because we are free to choose whatever we want. So basically here is mainly focusing on the propagation method that we are using to be able later on to implement the similar concepts or similar methodology in a more realistic situation. So through this propagation, we have I find out that there is 2 main branches, what is called intrusive methods and non-intrusive methods. In our case, for example, it's an intrusive method because we need to reformulate or modify the solvers. For example, polynomial chaos, or there is other methods called perturbation method that is not that, how do you say, accurate compared to the generalized polynomial chaos that you use in a Taylor expansion. And from the size of non-intrusive method, that is, I would say, quite the most popular because require, for example, Monte Carlo, and does not require any reformulation of the solver. So it will be kind of completely independent of which solver are you using. See, here you can see some of the features, as I mentioned, which one require modification of the solver, the flexibility. Of course, generalized polynomial method will be limited to the specific solver that has been modified, and then the relative complexity in terms of the implementation of each of them. So this is something that I find out quite interesting, and I think I try to also highlight and try to share with the rest of the intended users of this project also. And it's pointed out that this discipline is relatively young, and also it's about focusing in practical problem applications. So that means that it's still remaining some kind of a theoretical unified way of doing things. In somehow it's good because you are free to try to fit your problem, but in somehow, and I already kind of observed that through going through the entire literature, was not even a consensus on the, of course, was kind of analogous all the way of describing things, but was kind of saying the same aspect or the same formulations, but in a different notation. And that was quite challenging for me. So it could be interesting to write something that they can show at least what are the different notations and so on. And that's what I was trying to do also in the report, that try to expose the reader or the final user with a different notation, so at least they're aware that things can be formulated in a different way, but with the same meaning. So for those who are not aware, I try to, this is a little bit maybe a show off, but it's also to point out my motivation. For those who are not familiar with the deflagration, as you can see, is a combustion wave that propagates at subsonic velocity. And I will show you a small, I hope you can see it. This is basically an enclosure chamber where you have a couple of obstacles, different size and number. And basically, we are igniting in one end and then toward to the other end, which is a vented deflagration in this case. And what we can see here is how the flame propagates. And the flame propagation or the flame front is tracked by the what is called the regression variable, which is 0 when it's completely burned, the mixture, and 1 when it's unburned. But what I'm trying to point it out here, that for example, in this case, what we are seeing here, and we are talking about uncertainty, how complicated can become this type of simulations. So as most of you already know, we start with some inputs, some model in the middle, and then some outputs, normally on a simulation. But things can become very complicated, and we can keep on the illustration or example of the deflagration. So let's assume that we have a storage tank with a hydrogen on a container, inside a container, and then suddenly, for any reason, a non-intended release happens. That will include some uncertainties due to this simulation. Then the dispersion, because this the gas will disperse and will introduce another type of uncertainties into the model, because maybe the mesh is not the same or it's not suitable for the release. Then you have ignition, then you have deflagration, and all of them are interconnected. So as you can see, uncertainty, and now I start realizing how complicated can be this problem of uncertainty quantification. Okay, but let's move on to the entire project. What was the objective of this project? The entire project objective was basically provide a background on the general polynomial chaos, develop a tutorial for modification and verification, and improving as much as possible existing solvers for adaptability and scalability. And the scope is, of course, as the title say, is the viscous-Burger equation for supersensitivity, and the actual solvers is Burger's form and GPC Burger form modifications on those. And of course, because uncertainty quantification, at least for this method, require a lot of pre and post processing, those tools will be provided on the files, and verification and uncertainty quantification at the end. So a little bit of background in terms of the methodology. So what is the problem? You already know what is the problem, but why this problem and how we approach it. So because I already mentioned the equation, but I didn't show any mathematical description of that. So as you can see here, we have the Burger's equation, the 1D viscous Burger's equation in its non-conservative form. And you can see, I highlight one of the terms. We have the time-dependent term, the viscous-dependent term, and the non-linear term, or convective term, which is in red. That was actually quite challenging in terms of the formulation, and also figured out how we need to implement it in OpenFOAM. And that way I highlighted, and you can see in red, it's a couple of terms that are highlighted in red only, but the nonlinear term is one of them. And so why is important this equation? So this equation is quite relevant in terms of the flexibility or versatility. We have a well-known exact solutions. We can model even nonlinear acoustic wave and shocks, and has been used in a lot also as a standard test for partial differential equations for evaluate solvers, and also the wide or broad applications fields that can have. So going back to the viscous Burger's equation in 1D, as you can see, something has been changed here. And this is because I have been expressing exactly the same equation, but in its conservative form, that will be more suitable for the implementation in OpenFOAM due to the final volume methods. But that is not a trivial thing, because I have been facing why for a few days, so figured out why things was wrong, and at the end, apparently that was the issue. And then what we have here are the specific case where we're dealing with the Burger's equation in a range from -1 to 1 in the domain -1 to 1x. And then we have the boundary conditions and the initial conditions. And in the boundary condition, if you look into the left boundary condition where u where x is equal minus 1, we have a 1, which is the nominal value, plus delta. And this delta is the perturbation. And in our case, we are going to deal with a perturbation which is going to be assumed to be uniform distributed, meaning that all the points will have the same probability of occurrence. So as the title mentioned, supersensitivity, but what was that supersensitivity? So the fact is that in this particular case of the Burger equation, even a small change on the nominal value, let's say in 10%, as you can see in this case, from a nominal value of 1 to a perturbation, added a perturbation of 0.1, can have a significant effect on the final result to the steady state solution. And also you can see also how sensible it is in terms of the viscosity. So that's why it's so interesting and challenging this equation. So going toward in the report, you will see that there is a deterministic and a stochastic, but due to the time, I will focus only on deterministic formulation. And I will show you here a big picture because I actually made this picture to myself to understand what I was doing and try to have the big overview of the procedure before even I can dig into the math. So we have a typical diagram where you have, the pre-processing, simulation, and post-processing. And in the pre-processing, we have everything deterministic. Basically, a single value is assigned for each of the parameters. And then we have toward to the right what is the boundary conditions. And those boundary conditions will be defined. The probabilistic model of the perturbation, in this case, is assigned as we wish because it's a canonical problem, but that will require some engineering judgments. And in this case, it's assigned to a normal probability distribution, which does not mean that always will be normal. It's just an example of illustration because that is the distribution that most people are aware of, or the shape is quite easy to identify right away. And then we have what is called the uncertainty parametrization, which will assign a random variable, chi, and in this case, it's going to be a standard normal distribution with a 0 mean and 1 of a standard deviation. And then we follow the simulations, and toward to the end, we have all the post-processing with the treatment of the uncertainty and the calculations, which will lead to an estimation or quantification of the mean value plus minus the standard deviation. And of course, the determination or the assumption about which type of distribution we will have in the solution, that will require further study that I have not been done this. So you will see at the end during the verification process that I just report the uncertainty from the standard deviation, because that will require to express the uncertainty as an expanded uncertainty will require further analysis. So how we implement the generalized polynomial chaos. So basically, first, we need to write down or expand the solution in terms of a spectral expansion or polynomial chaos expansion, where we have basically two terms. The deterministic term, the u hat sub I, and then we have the polynomial terms, which are the basis function, which are orthogonal. So, of course, we are not going to work on an infinite domain. So we need to truncate that. So that introduces some also approximation errors. And you can see here, I put those terms just for the sake of documentation. I'm not expecting that. But basically, we have chi, which is, as I mentioned, the random variable, which depends in another omega parameter. And chi can be the dimension of the number of random variables can be, depending on the problem. Of course, in this case, we are dealing with only one, but of course, can become more and more complicated. And as I mentioned, the polynomial, orthogonal polynomial basis functions, and then deterministic, and P is the order of the truncation. So why orthogonality and why we are using polynomial basis that has this property? And that will become very handy because actually the fact that they are orthogonal simplify a lot of the formulations for later on. So here we have basically the inner product of two of these polynomial functions which at the end turned out to be a gamma factor multiplied by the Kronecker delta. And that will simplify a lot, especially if we are normalizing the basis function. So basically, by normalizing, gamma factor become equal to 1. So at the end of the day, we simplify all the formulations. All the details in terms of the derivation is on the report. So here I'm going to give you just an overview. So it's not going to be a lot of math, just a couple of equations to point out where we are. So if we substitute this expression, basically the expanded solution into the Burger's equation, we will have this quite long representation of that. And then we need to do another step, what is called the Galerkin projection, which basically is the entire expression of the expanded random Burger's equation multiplied by, again, normally we do it for, again, multiplied by the same basis function. And then the feature or the property of this projection is actually that the residual between the SAC solution and the approximated will be orthogonal to the space defined by the basis function. And that will give the best approximation in that sense. So as you can see, I have a big jump here. So we are on the random Burger's equation, and suddenly I have already final solution. Is because the entire derivation takes some time, and I don't see you will gain much more on that. But at the end, after a couple of applying the orthogonality property, you will end up to a final system of equations. Which the good thing is that actually that's why it's called random. Burger's equation is because the equation is random, but the solution has a behavior as a stochastic, because there is some slightly difference between random equations and a stochastic equation. I'm not going to deal or going too deep in that sense. Because first of all, I'm not an expert on that, but keep in mind that this is a representation from the random equation. And basically what we end up here, it will be with a system of couple of equations, which each of them can be solved as if it was a deterministic system, as normally we used to do with a normal solver. So that is the good thing. And then we will have, depending on the order, +1, the number of system of equations that we need to solve. And then you may ask, okay, why, from where comes this Mij? And this is actually the quite important, which is the Galerkin tensor. And this is part of the pre-processing, because the good thing about this tensor is that we can pre-calculate it before the simulations. And those coefficients can be saved for future simulations. So, okay, I show you already the derivation, and now, of course, we need to apply boundary condition. I think that will be much easy to follow on the slides. So we have left and right boundary conditions, and in the left, as I mentioned, we apply or we impose a perturbation. So basically, we expand that expression in terms of the polynomials. And then basically the expression for the polynomials, and since we want to express the perturbation in function of the mean and its own standard deviation, we just need to expand to the second order. So basically the first and second term. So it's going to be only the phi 0 and phi 1. And that simplifies a lot. So this is from the definition of what is the mean and the standard deviation of a standard deviation or of a uniform distribution. And then finally, we will get the expansion coefficients. And those are the ones that we are going to compute with that we are going to impose on the solver when we do the cases, on the cases study. So here is a summary of the left and right boundary conditions, as you can see. The mean value, so it's going to be the nominal value plus the epsilon, whatever the value, in this case, we are going to give 0.1, plus half of that for the deterministic coefficient k equals 0, so it's a u hat 0. And then we have the standard deviation for u hat 1, and the rest of the other higher order terms, it will be equal to 0, because it's not going to give any contribution to the boundary conditions. And in the right boundary conditions, is quite straightforward, because we don't have any contribution for higher order terms. We only have the nominal value. So here is a little bit of what is going to be the post-processing part. I'm not going to the detail of how those equations has been derived, but basically to estimate the mean value of our final solution, everything boils down to work with the actually it's the value of the first mode that is the highest contribution, and you will see the contribution of the different modes when I show you the results. And the variance also is the summation of the square of each of the modes higher than 0, sorry, from 1 to p. So I will show you now the existing and modified solvers. What I boil down here is I will show you one slide with the existing solvers, and then I will show you what was the thing that I have been improved. And then for that, I'll say what are the challenges you will see, and why, or how do we modify the existing solver. So as you can see, the solver actually is based on a very basic solver, the scalar transportation solver. We have a simple loop, and then inside we have a big loop, which is for all u hat, or for all the coefficients that we need to solve. And then the special part is when we need to solve of course, we have the time. Can you see if I point it out with my, no. So basically we have the time-dependent component, which is solved implicitly, and also we have the viscous term also implicitly. And of course, when we are dealing with a nonlinear term, we are solving it here in a particular way. So for the mode that we are solving, the mode is solved implicitly. However, the other modes remains explicitly. So we are still working with the values from the previous time or iteration. And then we solve the equation, and we update the flux. So what you can see here, what is missing on this equation, I know sounds trivial, but that was a nightmare for me to figure out why I didn't get the right results. And it's missing this factor. That's quite simple to solve. And then, yeah. And this is how we end up the final version of the modify. And if you notice here, I added the factor, of course, 0.5, but also I added a smart point. And actually it was a very good suggestion from Said, actually, because I was missing that part, and I was ending up having a memory leakage. So I think it was a good lesson learned from that point, because in this case, the improvement was not significant. I couldn't see any drawbacks, but of course, when you are dealing with a bigger computation or more computational expensive codes, you might notice that the memory leakage can be an issue. And you can see why I'm talking about this asterisk E member. So, and you can see why it's defined in this way. This is the original creating fields H file. So, and the tensors actually was hard coded. So that means that every time if you want to change the type of a polynomial or increase the order of the polynomial, you need to change these values in this, and then compile the solver. So that was not the best, I would say, way of doing it. And on top of that, since this is the values of the tensor of the Galerkin tensor, there is this property of sparsity. So a lot of the values are 0. But in this case, it was not even initialized. So I noticed that when I start doing some calculations, some values was assigned randomly by OpenFOAM. So what I did, as I say, by suggestion of Said, I implement this auto pointer, which is a smart pointer. So basically, the memory will be allocated, and after when the variable is getting out of the scope will be released or liberated. And the good thing of this implementation now is that actually we are already dynamically associated the structure of the tensor with respect to the order, because we have a file called UQ properties, where the order of the polynomial expansion will be reported there, and then it's read. That's why we need to use not only chaos pi for the calculation, but also PyFOAM. PyFOAM. So, and this is how we read the implementation here might be improved in the future. I don't know. I just use a loop. That was the easy way for me to understand what I was doing. But basically, it's reading and populating all the values from the constant folder on what is called the GPCcof, which is actually a file that we create previously before the solver is running, or the simulation start running. And those files are generated automatically based on the type of polynomial. In this case, it's only Legendre polynomial, but also in terms of the polynomial order. So for the pre and post processing, the post processing tools, you can see it on the report, but the pre processing tool, I think, are the most interesting right now. So as you can see, there is several steps, because for me, it was my first experience to work with the chaos pi. So I didn't trust myself in that sense. So I made some kind of a double check or sanity check verifications that the implementation that I was doing was correct. So, but the main point actually is the first one, which is generating the distribution and the polynomials, and the third, which is the calculation of the tensor coefficients. So to calculate the tensor coefficient, first before that we need to generate the polynomial and the distribution. So we use some embedded libraries from chaos pi. And one thing that I need to highlight here is also that the good thing about this implementation, as you can see, we have an if statement in terms of Legendre, and that Legendre will be read from the UQ properties, so it will be flexible to be expanded to other type of polynomial. It's just added a couple of lines extra, and then you will have right away Hermite polynomials or other types you want to work with. So that was also, I want to keep in mind the flexibility of the code, so for potential future improvements. And what we did here is basically create a standardized, which is in this case for the uniform is from -1 to 1. And then one thing that is relevant here, yes, that normed, which is actually the normalization part, need to be true. And then physics, because some of the factorization is different if you use a physics method. So that is something to point out. And then we calculate the coefficient. Basically, it's just the triple product of the polynomials on a loop, and then we use a Gaussian quadrature to calculate the values. So the verification and uncertainty quantification. So as you can see here, this is the structure of the case studies. So actually, we have two main studies. One is the deterministic, and the other one is the stochastic. Today, we are going to focus only on the stochastic, which is, I think, the most interesting. The other one was for myself, and also to do kind of a cross comparison with the results, as you will see, because we have in the stochastic, in the last red circle, we have three cases. The stochastic verification 1 and 2. One is for the lower boundary, and the other is for the upper boundary. And the third one is for the uncertainty quantification. But first, let's focus on the verification ones. Those two, actually, the interesting part is, even if we have a solver that is meant to be for having a stochastic solution at the end, you can use it. I'm not saying it's the most efficient, but you can use it still as almost like if it was a deterministic. You just need to put the rest of the higher order components equal to 0, and we are making work in the solver as was intended as a normal OpenFOAM solver with no any uncertainty. And that's what I was checking against the exact solution I will show you now. So this is how we configure the stochastic solve. Sorry. This is how we configure the stochastic cases. For the case number one, basically what we define is what is the values of the perturbation. So for perturbation, one is equal to A, which is the lower bound of the domain is equal to 0, so no perturbation. So that will give us the lower boundary of the results. And then when we put it equal to B 0.1, we will have the higher part. And this will should match the result with a steady state exact solution. And then in the third case is when we implement for the U hat 0, which is the first coefficient or the deterministic coefficient. We will place it the perturbation equal to the mean value of the uniform distribution. And then for the U hat 1, which is the next order in terms of the deterministic coefficients, we need to use in the case of in both of them, we set it as 0 in the deterministic cases because we don't want any contribution for higher order terms. But in the uncertainty quantification, we assign the value of the standard deviation of the uniform distribution. So the execution has been made quite simple because the user will have to only run all run script and all clean, and that has been learned through the both courses, the preliminary course and the advanced, or the basic course, and I think that was a very nice learning process. So I make a type of code that I can replicate and keep reusing it, and I think that was but basically everything runs automatic fashion, and that's why the structure, in my case at least, maybe something that I will need to learn in the future, but it's very tied to the structure of the folders. So everything is connected. So even the names and the number of folders that you have inside will be related to all the process that happen, post-processing and pre-processing. So this is the result for the verification. As you can see, well, you cannot see actually the exact solution and the simulation because they are overlapping to each other, but you can see on the relative error that is still there's slightly some minor differences, I would say, and it's actually around the transition layer. And then we compare the result from the exact solution and the stochastic solution at the exact transition layer with a perturbation of 0. We will get down to the 7-digit agreement, and then for a perturbation of 0.1, the same level of agreement with the exact solution. That was quite nice, but that took me some time because I need to figure out that the conservative form was the way to go in this case. And this is for the uncertainty quantification. Here, what we have here is in the lower bound, which is actually the result from the previous slide, and then we have the upper bound, and in the middle we have the mean value, and then we have also the shaded area, which is the mean value plus minus the standard deviation, due to the fact that the symmetry, the standard deviation is basically the average of the deviation around the mean. And what you can see here has been comparing the results for up to polynomial order of 3. And we compare the result with the documented, actually is the main article we are trying, or I'm trying to kind of replicate. And they have been using a different method. They have been using a quite high accurate method with a spectral method. And we went down to 6 order or 6 digits of agreement with our results. So some conclusions. A tutorial has been developed, and that hopefully we can keep building in top of that, and implementation of modification and verification of both solvers. And yeah, hopefully this will support improvement and expansion of UQ in OpenFOAM. And future work, at least from my point of view, I think would be nice to implement in more complex situations. And in my case, I will be try to do if I can do something regarding hydrogen deflagrations. All the references are here, so in case someone is interested. Thank you.